Hello, everyone. Thank you very much for watching this KiboCUBE Academy on-demand pre-recorded lecture. This is the second edition of the lecture number 06, Introduction to CubeSat Design for Safety Requirements. My name is Toshinori Kuwahara, Associate Professor at the Department of Aerospace Engineering of Tohoku University, Japan, and also the Chairperson of UNISEC, Japan. My research topics are space development, utilization, and exploration by small spacecraft technologies. Now let's start the lecture. Here is the overview of this presentation. So first, I will start with an CubeSat system engineering process and move on to safety and mission assurance activities, safety design process, safety design of CubeSat, documentation and ground testing, and CubeSat mission assurance, before concluding my presentation. The first chapter is an introduction to the CubeSat system engineering process. To ensure safety and mission assurance of CubeSats, it is important that we understand the system engineering process first. When a CubeSat mission is initiated, the project will follow these satellite design, development, and verification processes. The processes themselves are shown on the left side, while the middle section details the design and verification reviews, and the right side is the output from the process. The first step is the mission analysis and design activity. The output of this activity is the mission definition of your CubeSat project. The contents of the mission definition are reviewed by way of a mission definition review, also known as MDR. If the project passes the mission definition review, then the project proceeds to the next step. The steps that follow also work in a similar way. The second step is the system analysis and design. And the output of this system analysis and design is the system definition. The result is reviewed by a system definition review, or also known as SDR. The next step is the preliminary design activity. In this activity, it is often the case that the prototype of satellite components are developed and tested in a so-called breadboard model level. The results of the preliminary design is reviewed in the preliminary design review, or PDR. Then the next step is the detailed design process. Though it is called a design process, this is a step where the manufacturing of the engineering model of the satellite starts, and the design and the functionalities are tested. So therefore, the output of this activity is the development and verification of the engineering model, which is also called as EM. The result of this detailed design process is reviewed in a critical design review, or CDR. After that, the manufacturing of the flight model of the CubeSat will be finalized, and the manufactured flight model is then qualified through flight model testing. The output of this activity is the satellite flight model, or FM, and the results are reviewed in a qualification review and launch readiness review, etc. The definition of these reviews is dependent on the specific satellite project. And now your satellite is ready to be launched. So you can see there are many steps in the design process, and each step requires a review to produce an output, as illustrated in this slide. So now I'd like to explain the blue arrows on the left. The first one is indicating the requirement definition process. The requirement definition process starts at the very beginning of the project and shall be finalized by the preliminary design review. The second arrow is indicating the system definition process of the satellite. The process shall start at the system analysis and design activity and shall be finalized by a critical design review. Then the last arrow is the verification process, which starts at the preliminary design process and shall be finalized by a qualification review. So the first two activities can be regarded as a top-down engineering flow, and the last one can be regarded as a bottom-up engineering flow. This is called the V-model engineering process. It is also important that we understand each activity in the V-model engineering process. So I'd like to begin detailing the first step, the mission analysis and design process. As I roughly explained in the previous slide, the input to this activity is the mission objectives. And the outputs are the mission requirements, such as functional requirements, operational requirements, and constraints. It is important to note that many of these requirements and constraints are derived from the safety assurance aspects of the project. Typically, mission constraints are also listed here. They are the launch opportunities, such as mass properties, size, launch environment, orbit, etc., schedule cost, human resources, development facilities, interfaces, regulations, the space environment, and so on. The relationship between the satellite and the surrounding environment is described on the right-hand side of this slide. So we need to take into account the interfaces between the satellite and ground support equipment, test facilities, launch vehicles, and ground stations, and so on, before moving on to the next step. In this slide, I have summarized the engineering aspects of system analysis and design as the next step. The input of this activity is the mission requirements defined in the previous process, and the output is the system definition as mentioned in the previous slide. The system definition includes the preliminary mission concept, satellite orbit, number of satellites, payload instruments, satellite bus systems, launch vehicle selection, operation planning, ground station, ground support equipment, and so on. As for the definition of payload instruments, we need to consider the engineering aspects such as the types of instruments, that is, whether it's communication instruments or optical observation instruments, and so on. The acceptable mass and size requirements, power consumption, voltage, telemetry data, mission data, command data, thermal control, actual pointing accuracy, operational constraints, and so on. As for the bus system, we need to define the allowable mass, size, power consumption and generation, actual control, telemetry data, command data, computational capability, communication capability, thermal control capability, orbit control, propulsion, autonomy, and so on. I hope this helps you understand there are such a wide range of different engineering aspects to be discussed when designing a spacecraft, even if it's very small in size, such as a CubeSat. These engineering aspects will fall into the categorization of subsystems that can be defined in the way you see on this slide. So please remember that a satellite can be described as a composite of subsystems, which are classified according to functionalities and interfaces between them. For the satellite system integration, it is very important to understand the interfaces between these subsystems and their components. As I already mentioned, all subsystems except the payload system are denoted as the satellite bus system. It is also very important to understand the relationship between the payload and the bus system. With this understanding, I'd like to explain about the satellite system design process in general. The satellite system design process is an iterative design refinement and verification process. During the process, satellite system sizing and budget control should be conducted through engineering trade-offs, which includes managing several system budgets as listed here. They are mass budget, including mass probability, power budgets such as power consumption, generation, and storage, size budget, communication budget, data storage budget, computational budget, operational budget, financial budget, and schedule budget, and so on. You need to take care of all these different aspects by yourselves as a project team. So I'd like to say that the satellite systems design is a sort of art in itself. The illustration on the right-hand side explains this iterative design process of the satellite. Firstly, in the preliminary design process, which is indicated as the biggest gray circle in this diagram, you try to define the first sketch of the satellite system iteratively. If the preliminary design passes the preliminary design review, or PDR, the project can move on to the next step, the detailed design, verification, and qualification. As I mentioned, the detailed design process will be followed by the critical design review, and then according to the critical design, you can finalize the flight model design. Finally, the flight model is manufactured based on the finalized design, followed by verification before the flight model can finally be launched. This process through the BBM, EM, and FM is illustrated in this figure as an arrow. The design accuracy gets improved in each design process. So it is very important that the flight model design is clearly defined in the previous EM process, and you don't need to change the design of the FM from that point forward, especially in terms of the verification aspects. So small satellite projects can offer the best hands-on space engineering education to new developers and young engineers. So project members and students can obtain a broad real-life experience, beginning with initial satellite engineering activities, such as mission analysis, system design, system development, and component procurement, etc. So development activities tend to follow such as component development, system integration, onboard software, algorithm development, ground verification, and ground environmental testing. So in addition to these activities, some project management aspects, such as safety design, safety review, satellite delivery and launch are also important topics that you may be exposed to. And then finally, operational activities such as ground station installation, satellite operation, instrument calibration, and satellite data analysis can also be expected. So there are some exemplary pictures from satellite projects. So if you experience all these activities once through a smaller satellite project, for example, through a CubeSat project, that knowledge can be applied to larger satellite projects with a strong confidence. So as we look through the overview of the CubeSat system engineering process, I'd like to next discuss the safety and mission assurance activities for CubeSats. The safety and mission assurance activity is also known as S&MA. It is a very important system engineering concept, finding a solution between two different subjects, safety assurance and mission assurance. So I'd like to introduce these terminologies one by one. Let's start with mission assurance. For mission assurance, satellite projects shall conduct activities to maximize the probabilities of mission successes by mitigating any risks that threaten mission success, such as design failure, production failure, test and verification failures, etc. Whereas safety assurance is an activity to fulfill any safety requirements criteria of the system. The safety design requirements necessitate that satellite systems be equipped with multiple inhibits against hazards to ensure safety in the surrounding environment of the satellite. So in some cases, this could result in excess restrictions of the satellite functionalities. So here, an inhibit is defined to be a design feature that provides a physical interruption between an energy source operating a function leading to an accident and an operating device. So understanding these terms, safety and mission assurance is the activity combining both safety assurance and mission assurance. A satellite project shall find the best balance between safety design and mission assurance within the limited resources of the satellite system, as well as the project, by keeping the mission success probability as high as possible. Therefore, you will need to conduct a system design engineering trade-off between the mission assurance and safety assurance. Now let's take a look at an example of a safety and mission assurance activity and the influence this has to the satellite system design. So safety assurance and mission assurance are often design drivers of opposite directions. It is very challenging that both aspects are satisfied in the limited resources of the small satellite system, especially considering their small mass and envelope size. Now, please take a look at the figures below. The left-hand side is illustrating the original design of the electrical switches between the power source and panel deployment mechanism. The panel deployment mechanism is, in general, regarded as a potentially catastrophic hazardous mechanism of a satellite system, as it can harm launch vehicles and ground personnel during the assembly, integration, and test of ground. Then in the mission assurance activity, described in the middle of this figure, satellite engineers often try to duplicate this electrical switch to be redundant in order to ensure that the panel deployment mechanism can be deployed even in the case should one of the switches fail in orbit. However, on the contrary, the safety assurance activity goes in the opposite way. the system engineering activity in safety assurance tries to implement multiple switches in series. So in this case, 3 switches in series, as the hazard can be classified as a catastrophic hazard, in attempt to ensure that the panel deployment mechanism is not deployed during the launch and ground activities, even if 2 of these switches fail at the same time. So in this design, these electrical switches are called inhibits with respect to the idea of redundancy. But if you have 3 switches in series, all of these switches need to work properly when you want to open the deployment panel in space, which infers that we are reducing the mission success probability. In general, the trade-off study between the safety and mission assurance activities ends up with the solution as illustrated on the right-hand side of this figure. So you try to avoid any unwanted panel deployment by utilizing 3 switches in series. And in addition to this, you prepare redundant sets of these switches so that even if one of the switches fails, you can utilize another power supply line to open the deployment panel. Now you can then compare the leftmost figure and rightmost figure. The original design included only 1 electrical switch, but after the safety and mission assurance activities, you now have 6 electrical switches, which means you are adding mass and reducing the spatial resources in your satellite. I hope this example helps you appreciate the importance and the challenge of conducting safety and mission assurance activities. So in this sense, reducing the number of components by ensuring the reliability of each component and eliminating a redundant design as much as possible is a key design approach for small satellites with limited resources. In terms of the safety design of the satellite system, satellite development project shall consider safety design aspects for the entire project life cycle. I have listed the project life cycle phases and the related safety design aspects below. In the development and handling phase on ground, you need to consider safety aspects against the ground facilities and equipment, personnel, and transportation, etc. So in the next satellite launch phase, the satellite shall be safe against the launch site, launch vehicle, and other satellites being launched by the same vehicle. This is illustrated in the figure on the right. Similarly, for satellites deployed from the International Space Station, they shall be safe against the International Space Station and the astronauts. So finally, in the operational phase, safety design shall consider the International Space Station and other spacecraft in near orbit, the space and Earth environment, and human beings on Earth. This is also illustrated in this figure. So in this way, the safety design requirements for satellites depend heavily on launch vehicles and release systems. And the safety design plan, implementation, and the verification results shall be confirmed by a safety reviews by the related organizations. You also need to be aware that the safety design requirements can greatly affect the system design of your satellite, and hence they shall be considered from the very beginning of the satellite project. In the following slides, I'd like to introduce CubeSat-related design standards, as well as the launch and the release environment and requirements, in order to clarify the safety requirements imposed on CubeSats. So this is one of the world's first CubeSats, Sci-4, developed by the University of Tokyo. And the figure below is illustrating the dimensions of one U CubeSat. The current related standardization of CubeSats is summarized in this slide. So the first one I introduce is the CubeSat Design Specification Lev 113, organized by the California Polytechnic State University. So it is publicly available under this link. So this standard provides a basic idea of CubeSat. So I recommend that you are informed about it as the first step. And there are several more working documents available in the community. The second one I will introduce today is the CubeSat System Interface Definition, organized by UNISEC Europe. So this standard suggests interface definitions for the internal electrical components of CubeSats. So this is available here. There is also an ISO standard covering the CubeSat satellite itself, as listed here. There are also ongoing activities towards international CubeSat interface standardization. The last one is the GEM Payload Accommodation Handbook, Vol 8D. So released by JAXA. In terms of the KiboCUBE program, this handbook, which is also known as JPA, will be the most important document and guideline for you. Here, JEM stands for the Japanese Experiment Module, which is another name for the Kibo module. The Japanese and English version of Lev-D are available here. So in addition to them, JAXA also has general common technical documents available in both in English and Japanese here. So if you would like to deepen your knowledge about space engineering further, please refer to these technical documents as well. So as you might be already informed, KiboCUBE provides deployment opportunities from the ISS. In this framework, the possible launch vehicle can be one of the transfer vehicles to the ISS, which are Japanese HTVX, the H2 transfer vehicle, Dragon spacecraft of SpaceX, and Cygnus spacecraft of Orbital Sciences Corporation. The launch environment is different in each vehicle. So CubeSats are installed in the satellite deployment pod, so J-SSOD, Japanese Experiment Module, JEMU, Small Satellite Orbital Deployer, J-SSOD, and stored inside a cargo transfer bag, or CTB, with soft packing materials. So the vibration conditions are very mild relative to those encountered during direct launch. The frequent launch opportunity to the ISS are provided up to 4 times per year in general. As the orbit altitude where the CubeSats are released is about 400 kilometers, it is ensured that the CubeSats will re-enter the Earth's atmosphere after their mission lifetime without becoming space debris, thanks to the Earth's atmospheric drag from the relatively thick atmosphere in that orbit altitude. And actually, the radiation condition in this low Earth orbit is mild. So these features can be great benefits to new CubeSat developers. So on this slide, I have summarized the CubeSat deployment opportunities from Kibo. So Kibo provides options of J-SSOD in 3 different forms: so 3U, long 6U, and wide 6U. So consequently, there are these kinds of form factors of CubeSats. which you can utilize for your own project. So they are 1U, 1.5U, 2U, 3U, 4U, 5U, as well as long and wide 6U. So it's possible that your satellite is stored into the pod together with satellites developed by other project teams. So you can select the most appropriate form factor for your CubeSat missions, so depending on the mission requirements. So let's also take a look at the mechanical conditions during the launch. The possible launch vehicles and the transfer vehicles are HTBX, Dragon, and Cygnus. The random vibration conditions of these vehicles are summarized in this table, which are also visually illustrated in the figures as well. As the KiboCUBE Academy CubeSat are stored inside the cargo transfer bag, or CTB, with soft packing materials, the random vibration condition is milder than that of a direct launch into orbit by other typical launch vehicles. And also, there is no shock requirement. This means that unlike a normal launch by a rocket, you can ignore shock conditions during the launch and transfer. The quasi-static acceleration condition differs depending on the vehicle. So HTB is the mildest at 6.0, and the other two vehicles are 9.0G. So detailed information is also available from the reference link below. So please take a close look at them. And also please note that according to the newest specification information, the random vibration condition of the SpaceX Dragon spacecraft was updated as summarized in this table and as illustrated in this figure. So please make it sure that you refer to the newest information. Now then, let's take a look at the other important environmental conditions as summarized in this slide. The handbook specifies the maximum air pressure changing rates, temperature conditions, and humidity conditions. The CubeSats are stored inside the vehicle in a pressurized compartment during the launch. One of the important aspects I'd like to highlight here is the air pressure changing rate inside the GEM airlock, just before the release from the ISS. So your satellite structure needs to have venting holes for venting out the atmosphere inside the satellite during the vacuuming process. Another important aspect is the temperature condition outside ISS, while your satellite is inside the J-SSOD, awaiting release from the ISS. At the end of this chapter, I'd like to summarize the relationship between compatibility, safety assurance, and mission assurance. So space systems, including CubeSats, are required to satisfy compatibility requirements of the corresponding launch vehicles, such as mass, size, environmental conditions, etc. Safety assurance activities are applicable within the scope of this compatibility compliance, which imposes further and more severe requirements to the space systems. So mission assurance activities are applicable within the scope of safety assurance compliance, which attempts to achieve desired system reliability by managing resources of the space systems, retaining a portion of as a spare for introducing redundancies and or even more design margins. So this relationship is illustrated in the diagram below. So your space systems need to fulfill these different kinds of requirements to be launched and to achieve mission objectives. As the satellite system resources are limited, comprehensive design trade-offs are indispensable to maximize the possibility and capability of mission assurance. In the next chapter, I'd like to explain the safety design process of a CubeSat, which is the main topic of this lecture. As I briefly introduced in the previous slides, all satellite projects need to pass several design reviews. Those required reviews are listed up in this slide. The first one is the JAXA-NASA safety review. So satellites to be launched by Japanese launch vehicles and or to be released from the ISS through JAXA need to pass the related safety reviews organized in several steps, starting from phase 0 to phase 3. A safety assessment report, or just SAR, shall be submitted to JAXA for the reviews. Satellites are required to fulfill safety design requirements described in JAXA's standard documents. I have picked up some of the most relevant ones below. So these are JMR001C, System Safety Standards, JMR002D, Launch Vehicle Payload Safety Standard, JMR003D, Space Debris Mitigation Standard, JXESPC 101133D, GEM Payload Accommodation Handbook Ball 8D, JERG 1007E, Safety Regulation for Launch Site Operation, and JERG 2025, Hazard Analysis Handbook for Small Satellites in Japanese, and JERG 2213A, the insulation. So please be informed about these documents very well. The second one is the Japanese Cabinet Office Safety Review. So satellites with Japanese nationalities and or operated from Japan need to undergo the safety review by the Japanese Cabinet Office. The third one is the JAXA Compatibility Verification Review. This review provides confirmation of the compatibility of the satellite verification results with the requirements from JAXA before delivery. So in this way, the safety design of all satellites to be launched need to be confirmed. So please consider that all satellites are subject to safety design. In the system safety standard of JAXA, available in the link below, the precedence of safety design is described as summarized in this list. So among the possible safety design measures listed here, we can basically consider that the first three are the practical approaches for small satellites, which are designed to eliminate hazard, designed to minimize hazard, and designed to control hazard. So in addition to these, there are several more possible measures for larger space systems and ground stations. These are use of safety devices, use of protective devices, use of warning devices, and application of hazard control method relying on special procedures and or training. So CubeSats to be released from the ISS are basically required to apply the above mentioned 1, 2, 3 approaches for their safety designs. So satellite projects are responsible to conduct system safety program activities throughout the entire life cycle to ensure safety related to the systems and to minimize and keep risks within an allowable level throughout the design, manufacture, test, and operation phases. So in this slide, I'd like to explain the safety review process for small satellites launched and released from the ISS. The safety design reviews are arranged in 4 phases, from phase 0 to phase 3. First of all, in phase 0, the system safety program plan shall be established and a hazard analysis shall be started to identify hazards. In phase 1, the detailed safety requirements shall be established and any inferences or measures of system hazards shall be examined. In phase 2, a detailed safety assessment shall be conducted and design compliance with the safety requirements shall be verified. Additionally, safety-related verification tests shall be conducted and the results shall be reviewed. In phase 3, the results from the verification of hazard controls shall be clarified, and it shall be confirmed that all safety verifications have been completed. So this phase is also where operational procedures shall be prepared, including emergency measures, handling, storage, and transportation, etc. The details of these definitions are described in the reference document below. In this slide, I'd like to explain the relationship between the satellite development schedule, design reviews, and safety reviews. This is an exemplary Gantt chart of a project schedule. First of all, the satellite models to be developed in the project are identified in the above row of the chart here, such as BBM, EM, FM. And then in the second row, the schedule of the design reviews relative to the satellite development models are illustrated here. After the project initiation, design reviews such as MDR, SDR, PDR, CDR, QR, LRR are placed before the launch. Here, the definition of the names of the reviews depends on each organization's custom. For example, the qualification review is sometimes known as a post-qualification review, or PQR, and the launch readiness review, or LRR, is sometimes known as a pre-shipment review, such as PSR, etc. In the third row, the schedules of the safety reviews are illustrated. So in general, phase 0 to 3 correspond to the SDR, PDR, CDR, and QR. So usually, safety reviews for small satellites are planned after the corresponding design reviews. So also, it is often the case that safety reviews of several phases are held at the same time. For example, you can possibly arrange to hold safety review phase 0 and 1 just after the PDR, or phase 0, 1, and 2 just after the CDR. So it depends on the project schedule and the technology readiness level applied to the satellite. The relationship among the system engineering activities is also illustrated below. As discussed in the previous slide, the requirements definition activity starts at the early phase and ends at the preliminary design review. The system definition phase starts at the SDR and ends at the CDR. So as indicated, both of these activities are conducted in a top-down manner from the system to subsystems and components. So the verification and production starts around the PDR and ends at QR. This process is, on the contrary, conducted in a bottom-up manner from components to subsystems and the overall system. So in this slide, I'd like to introduce the definition of standard hazards and unique hazards. Safety design begins with identifying the possible sources of hazards. Hazards can be classified into standard hazards that are common for general satellite systems and unique hazards that are unique for each satellite system. In the left figure, standard hazards are listed. So these are flammable material, material off-gassing, dust, toxic or biological hazardous material, sharp particles, exposure to mechanical hazards and translation path obstructions, exposure to touch temperature exceedances, exposure to light amplification by stimulated emission of radiation and or incoherent electromagnetic radiation emissions, exposure to noise limit exceedances, injury damage as a result of improperly bonded and grounded equipment, injury damage as a result of improper power distribution circuitry and circuit protection devices, mating and demating of energized connector, non-ionizing radiation interference, injury damage as a result of rotating equipment failure, and injury damage as a result of sealed container failure. Also in the left figure, some of the unique hazards are listed, such as leakage of electrolyte or rupture of battery, a collision of the deployed CubeSat with structure failure against the ISS structure, a collision of the deployed CubeSat with inadvertent deployable part against the ISS structure, etc. So let's discuss a little bit more about unique hazard. The satellite development team is responsible for the identification of unique hazards, which are specific to each satellite, as only the project team knows about the detailed design of the satellite. So hazard identification shall be performed throughout all phases. A hazard identification table shall be prepared at the beginning of the project phase, and it shall be updated as the design matures. It is very important that engineers shall be honest in their safety design activities, as it matters to consider the lives of human beings. Here I have an additional list of the possible unique hazards. These are structure failure, deployment mechanisms, shuttable materials, glasses, etc., handling of heavy items, specifically utilized for the satellite, such as the satellite itself, transport container, etc., electrical short circuit of batteries, propulsion systems, pressurized systems, unexpected radio frequency emissions, and so forth. When you identify the safety hazards of your satellite, the hazard severity level shall be classified into the following 4 categories. The category 1 is defined as a catastrophic hazard. A catastrophic hazard is defined in the way that it can cause death or severe personal damage, or has an irreversible or significant environmental impact, or poses loss or severe damage to public or third-party properties, or loss of a system, such as the International Space Station and launch vehicles or launch site facilities. Similarly, Category 2 is defined as a critical hazard. A critical hazard is a hazard that can lead to major personal damage or reversible significant environmental impact or major change to public or third-party property or severe damage to a system or launch site facilities. The third category is a marginal hazard, which can lead to minor personal damage, reversible moderate environmental impact, minor change to public or third-party properties, or major change to system, major damage to system. The last category are negligible hazard, which are any conditions that cause less significant damage than that posed by the level 1, 2, and 3 hazards. After the classification of the hazard severity level, as described in the previous slide, a risk assessment shall be conducted as the next step. So risk assessment criteria is based on the combination of level of damage and likelihood of occurrence. So this is illustrated in the figure below. The left-hand side is the classification of the hazard severity level, and above is the classification of the likelihood of the occurrence. The hazards classified into the red area are distinguished as an unacceptable double risk. So those in the yellow area require individual decisions whether they shall be treated as unacceptable or not. So those in green areas are regarded as acceptable hazards. So safety design shall be applied in order to control unacceptable hazards and reduce the likelihood of their occurrence. So in general, the safety design approaches to be applied to CubeSats are the fault tolerance design and design for minimum risk. So in the following slides, I'd like to explain both of them one by one. The first one is the fault-tolerant design. The following fault-tolerant design requirements shall be satisfied to control hazards and reduce the likelihood of their occurrence to an allowable level in accordance with the hazard level. So rule number 1 is that a double failure or a combination of one failure and one human error and double human errors shall not cause a catastrophic failure. This is rule number 1. And rule number 2 is that one failure or one human error shall not cause a severe accident. So this is illustrated in the figure below. So the above mentioned rules indicate that for catastrophic hazard, we need to implement 3 inhibits so that double failures do not cause a catastrophic failure here. Similarly, for critical hazards, we need to implement 2 inhibits so that one failure does not cause a critical failure. So next, I'd like to explain the idea of design for minimum risk. For some design cases, fault-tolerant design cannot be applied, such as structural design or pressure vessels. So in these cases, design shall be managed by considering sufficient design margins, safety factors, and appropriate selection of materials and parts. So the figure on the right side here explains the comparison between the 2 design approaches. The fault-tolerant design can be understood in the way that it prepares 3 inhibits to prevent the hazards, with the assumption that those inhibits can fail. Something like this. On the contrary, design for minimum risk can be understood in the way that it utilizes a thick and strong enough barrier which doesn't fail as a preventative measure, which is something like this. The appropriate design fields of design, the applicable design fields of design for minimum risk are the structure, pressure vessels, pressurized piping and joints, pyrotechnic devices, material flammability, safety critical mechanisms, material compatibility, etc. That was the safety design process. And now we'd like to move on to the next chapter, safety design of CubeSat. This chapter provides some lessons learned of safety design examples of small satellites. These include safety designs related to separation switches, electrical circuits, such as double insulation, remove before flight pins and flight connectors, deployment mechanisms, and wire mechanisms for deployment structures. The discussions in the following slides are design examples, and I need to emphasize that safety design of satellites depends on each satellite. So please be aware of that. In this slide, I'd like to explain about the importance of separation switches from the safety design point of view. So separation switches are also called as deployment switch, as they detect the deployment of CubeSats from the release pod. In general, a CubeSat has different kinds of common catastrophic hazards. Some of these are listed below. For example, a structural failure, battery failure, radio frequency radiation, deployable structures, antenna, solar panels, etc., and the mission-specific failures. The first and second ones are discussed in other KiboCUBE Academy lectures, as indicated here in detail. So strategic electrical safety design is to use separation switches to control as many hazards related to electrical power supply as possible. This idea is illustrated in the figure below. The possible hazards are illustrated in dark yellow, with an electrical power source indicated in red, and satellite components illustrated in blue. As indicated in this slide, the electrical power source is separated from the left side with the 3 separation switches. In this way, hazards 1 and 2, which are RF radiation and deployable structure, respectively, are controlled in a double fault-tolerant manner. Then let's think about the safety design criteria for the hazard 3, which is related to mission-specific functions. So in this example, there is an additional switch between the component and hazard 3. So this could, however, be regarded as a supplemental function in terms of the explanation of safety design with respect to the safety requirements described in previous slides. By utilizing the separation switches in an efficient manner, safety design of the satellite system can be simplified. So it is also important to note that one of the 3 inhibits are recommended to be placed at the ground return line as indicated in the figure. This slide is illustrating an actual design example of the separation switches in the 3U CubeSat OrigamiSat-1 deployed by the Tokyo Institute of Technology. A CubeSat, or a small satellite, is equipped with several typically 3 mechanical separation switches, so that it can be securely powered off while it is stored in the release pod. The mechanical switches can be directly inserted in the main current stream or can drive other electrical switches, such as FET switches. In the former case, the relatively large current flows through the switches, and in the latter case, little current flows through the switches. So this figure illustrates that in the stored configuration before the release, the switch is pushed down by a pin, and pins are located at corners inside the rails. Then, in the following slides, I'd like to discuss safety design related to the electrical circuits. In general, there are 2 electrical power sources for CubeSats. One is the solar cells, which generate large volumes of power in space, but still generate small amounts of power at ground facilities. Solar cells are disabled for CubeSats during the launch and release from the ISS. Another one is the battery, which is subject to safety control even during a cold launch. So overcharge and over-discharge are also regarded as hazards, as the battery could become too hot and or explode. The safety design of the electrical circuit of the satellite should be valid for both of these electrical power sources. This is illustrated in the figure below. The 3 red lines indicate the possible current flows inside the satellite. The power generated by the solar cells is used for charging the battery and or directly consumed by the satellite components. The electrical power charged in the battery can also be consumed by the satellite components. And therefore, the safety design shall take these into account. As you can see, there are several places you can insert electrical inhibits. Please think about the possible solution where you have triple inhibits for all these 3 current flow cases. I think you can now understand that there are many ways of implementation, but the question is how we can reduce the number of inhibits in total in order to reduce the system complexity and improve the system reliability as much as possible. The hazard control can be achieved in forms of electrical switches, protection ICs, double insulation, remove before flight pins, RBF pins, flight connectors, controlling computers, etc. As I mentioned several times, the actual design depends on each satellite. In the following slides, I will show you some design examples. So let's take a look at this safety design example of the electrical power supplies. The components are located in the same way as the previous slide. In this example, there are 4 switches implemented at the main control for the hazards. So these are the separation switches 1A, 1B, 2A, 2B, 3A, 3B at these positions indicated in blue. In this way, the power supply from the solar cells and the battery to the satellite components are both protected, with 3 previously mentioned main switches, and also the power supply from the solar cells to the battery is protected by 2 switches and the power control computer at the 3rd inhibitor. It is also important to notice that there are two flight connectors implemented above and below the battery, here and here. This is necessary to conduct recharging of the battery from the outside of the satellite, even just before shipping. So in this figure, the hazard is isolated with an additional switch here. This will be used when the satellite is turned on and operation is started, controlled by the power control computer or other satellite components. Again, this switch has the functionality of the inhibit of this hazard, but can be regarded as supplemental, as I explained before. So also, please pay attention to the position of the grounding mechanism. So in this example, grounding is done at this position to the satellite main structure. Then, let's think about the safety aspects during the satellite handover procedure at the ground facility. When handing over the satellite, separation switches are enabled before the insertion to the pod. So, which means that the separation switches are in the position of the release situation. Therefore, it is necessary that safety is also assured in this configuration as well by means of other hazard controls, such as flight connectors, RBF pins, additional switches, etc. So this is illustrated in this slide. Another important aspect is the hazard severity levels at the ground facility. If the hazards are regarded as a critical hazard, not as catastrophic hazard at the ground facility, unlike the launch, the required number of inhibits becomes 2, not 3. So in this example, that kind of situation is assumed, and therefore, the battery is protected with 2 flight connectors, and the solar cells are protected with 1 remove before flight pin and the power control computer. Also, in most cases, the power generation from the solar cells inside the ground facility can be regarded as low enough to drive the rest of the satellite. Or you could actively hide the solar panels with some cover materials if required, and this could be regarded as an inhibit. So depending on your safety design, you might need to implement more and more switches inside the satellite, as indicated in the right side of this figure. Satellite resources are very precious, and you need to do your best to eliminate unnecessary components from the satellite as much as possible. However, as I'm repeatedly mentioning, the actual safety design depends on each satellite and each safety design and review process. I would be very happy if you could understand that you need to be very strategic and creative in terms of the safety design of your satellite. Another important topic related to the safety design of the satellite electrical circuit is that you need to prepare test ports corresponding to the safety design. So this is illustrated in the figure here. So for health verification status of each inhibit for safety, test ports shall be implemented and accessible from the outside of the satellite in order to confirm that the inhibits are intact. This is performed through electrical measurements, such as the resistances of the circuits and the voltages between 2 test ports. The flight connectors can also be regarded as test ports and can be used to monitor the status of the battery as well as the charging of the battery. This was a discussion about the safety design of the electrical circuits. Next, in this slide, we'd like to discuss the safety design of the deployment mechanism, which is also another very important topic. All deployable mechanisms shall be designed to fulfill two fault-tolerant safety design criteria, as they are classified to be catastrophic hazard. So safety design approaches depends on the mechanism used, hardware resources of the satellite, and required reliability, etc. The figure below illustrates 3 examples of safety design implementation. Let's take a look at them one by one. The first example, design A, is based on the 3 deployment mechanism and corresponding electrical switches. The deployable panel deploys only when all these 3 switches function properly, and hence it can be regarded as a double fault-tolerant design. So this design belongs to the category of fault-tolerant design. So in this design example, a deployment mechanism and an electrical switch can be regarded as a pair, and the satellite is equipped with 3 of these pairs. And if one of these 6 components fails, the panel cannot be deployed. The second example, design B, is also based on the fault-tolerant design strategy. So in this example, 3 deployment mechanisms are used, just like in design A, but they are driven by a single power supply line with 3 switches in series. Any combination of 2 failures among these 6 components doesn't lead to unexpected panel deployment, and hence, this is also double fault-tolerant design. The third example, design C, is a combination of fault-tolerant design and design for minimum risk. When the design of minimum risk approach can be applied to the deployment mechanism, you will only need 1 mechanism as illustrated in the figure. From the electrical point of view, you will still need 3 switches for the fault-tolerant design, but in this way, we can reduce the required components from 6 down to 4. I hope these examples also gave you a hint about efficient and strategic safety design of your satellite. The next topic of this chapter is the wire mechanism, which is widely used in CubeSat design, especially for the hold and release mechanism of deployable structures, such as deployable antennas and solar panels. An example of deployable antenna implementation based on the wire mechanism is illustrated in the right figure. The edges of the wires illustrated by dark yellow lines in the figure are fixed to the tip of the antenna, and the tensions are applied by the tension mechanism. There are redundant heaters implemented in the way that they touch the wires so that either of the wires can be cut by heating. Here, the redundancy of the heater is not for safety design, but for mission assurance. So, wire mechanism safety design shall fulfill the requirements specified as below. So I'd like to explain them one by one. So first of all, more than 2 wires are required for one constraining object. Then the wires shall be tested as to whether it can withstand the expected maximum load by only one wire as a proof test. Also, the appearance shall be inspected after the proof test. The assembly procedure shall be carefully specified. Also, if contact between the wire and the other structure is inevitable, the contact surface of the structure shall be rounded adequately. Finally, if the wire mechanism has a knot, losing shall be prevented by adequate method. More information can be found in the reference document below, which is one of the document templates related with the KiboCUBE application. This slide shows the actual implementation of the antenna deployment system based on the wire mechanism. So this is the design example of the 3U CubeSat OrigamiSat-1 developed by the Tokyo Institute of Technology. In this example, the antenna is based on convex tape. The two convex tape antennas are wrapped around the satellite structure. The shorter antenna is wrapped first, followed by the longer antenna wrapped on top of it. Then the tip of the longer antenna is restrained with threads and fixed to the satellite body. The threads are burned out with nickel wires in space when the antennas are deployed. So you can see in the figure that the two wires are implemented as required, and both of them are fixed to separate fixing mechanisms on the satellite side to control their tensions separately. Also, you can see some guide flanges as mentioned in the requirements. I hope this can provide you with practical information about the implementation of deployment mechanisms for your CubeSat. The last topic of this chapter is the thruster system. Some of the recent advanced CubeSats are equipped with thruster systems. Thruster systems are utilized to change and maintain orbits as well as to deorbit the spacecraft. Technology demonstration missions are also often conducted to improve the performance of thruster systems for CubeSats. The 3U CubeSat Act-D of Pale Blue Incorporated was such a technology demonstration mission of a water-resist jet thruster system, which was released from the ISS on November 20, 2019, as illustrated in the below figures. A follow-up mission of this thruster system of Pale Blue Incorporated was on both the 6U CubeSat Equus, launched on Artemis 1 in 2022. So thruster systems need to fulfill safety requirements, which include various engineering aspects, such as the pressure tank, fuel materials, orbital maneuvers, not to crash against the ISS, etc. Thruster systems can be hazardous against the launch vehicle, ISS, and astronauts when an unintentional leak, explosion, misfire, or propellant happens. And therefore, it is necessary to properly identify related hazards. These hazards shall be identified in all related mission phases, such as launch, release phase, astronaut operation phase, and orbital operation phase. Satellites released from the ISS require a safety assessment even during the orbital operation phase. The CubeSat shall have a lower ballistic coefficient than the ISS to ensure their lower orbital altitude than the ISS. A keep out zone, or KOZ, from the ISS, which is defined as plus or minus 2 kilometers in the altitude direction and plus or minus 25 kilometers in the along track and cross track directions, shall not be penetrated by the use of thruster systems to avoid collision with the ISS. Identified hazards shall be controlled by applying countermeasures, such as applying a limitation on the continuous injection time to suppress the maximum delta V by implementing 3 independent timers, or waiting until the satellite altitude becomes low enough before starting the use of thrusters, so that the satellite will not enter to the KOZ zone, even if the maximum delta V is output. The reference document on this matter is this one, the Baseline ISS Safety Requirement document. When hazards are identified, their criticality shall be then analyzed in all related mission phases, such as launch and release phase, astronaut operation phase, and orbital operation phase. So this table summarizes the exemplary hazards of a thruster system installed on the CubeSat to be released from the ISS, together with their hazard level classifications. The left side is the definition of the phases, and these are the corresponding hazards to the phases and their hazard levels. I will explain each hazard one by one. The one in phase 1 is that debris from bursts of propulsion systems, such as propellant tanks, valves, can damage other satellites during the phase 1. And then for the second phase, the first one is that toxic propellant leakage from the propulsion system, such as propellant tank, valves, etc., can damage ISS or IVA, the intravehicular activity, crews. And the second one is that the debris from bursts of propulsion systems, such as propellant tanks and valves, etc., can damage ISS or IVA crews, which is the same as the above case 1.1. For the third case, 4 hazards are identified. The first one is that improper ejection of the propulsion system can alter trajectory and collide with ISS structures and visiting vehicles. The second one is that debris from bursts of propulsion systems may collide with the ISS and the visiting vehicles. The third one is that due to deformation of the propellant tank, it may interfere with the rails inside the CubeSat deployment mechanism, J-SSOD, preventing the satellite from being released at the specified speed and causing a collision with the ISS structures and visiting vehicles. The fourth one is a possibility of collision with ISS or visiting vehicles due to inappropriate operational planning. As described, in total 7 hazards are identified. In this example, all hazards are classified as catastrophic hazards. After hazard identification, it is then necessary to identify the root causes of the hazards and clarify a causal relationship with the hazards as summarized in the table below. So also attention needs to be paid to the fact that the hazard identification and root cause analysis needs to be based on the actual individual design implementation of the thruster system, as well as the satellite system, where the thruster system is to be implemented, for example, as illustrated in the figure above. So, as discussed in the previous slide, safety design methods such as fault-tolerant design and design for minimum risk shall be applied in a strategic and meaningful manner. For example, design for minimum risk shall be applied to the mechanical design, such as a pressurized system, whereas the fault-tolerant design shall be applied to the electrical design. The 7 hazard root causes identified here are listed from A to Z. I will read out them one by one. The first root cause is the physical failure of propellant tanks and surrounding components. The second one is the selection of propellants unsuitable for handling on board the ISS. The third one is the erroneous application of power to the mechanism due to an electrical failure. The fourth one is the contamination inside the valve due to improper dust control. The fifth one is the undesired thrust generation due to inappropriate design and manufacturing. The sixth one is the deformation exceeding the allowable range due to the launch and on-orbit environment. The seventh and last one is the inadequate operational planning. So in this table, it is illustrated that one root cause can be the cause of more than one hazards in different phases. After identifying the hazard causes, it is then necessary to examine each control method of the hazard causes. A single cause may require multiple controls, which requires a very careful engineering analysis. In this example, hazard control are listed up on the right side, which are corresponding to the hazard causes listed on the left side. I will explain them one by one. The control for the first hazard cause, the physical failure of propellant tanks and surrounding components, can be a structural analysis or environmental tests against acceleration, vibration, pressure, temperature, etc. The control for the selection of propellants unsuitable for handling on board the ISS can be use of non-toxic, non-flammable, and inert liquid fuel, as an example. The controls for erroneous application of power to the mechanism due to an electrical failure can be 3 inhibits by 3 separation switches during the launch and before release, and 3 inhibits by 3 FET switches after release. So 2 controls. The control for contamination inside the valve due to improper dust control can be dust protection measures for the valve openings. The control for undesired thrust generation due to inappropriate design and manufacturing can be confirmation of propulsion force through testing. The control for deformation exceeding the allowable range due to the launch and on-orbit environment can be a structural analysis or environmental tests against acceleration, vibration, pressure, temperature, etc. And finally, the control for inadequate operation planning can be a formulation of operation implementation plan. As summarized in this simple table, all the identified hazards discussed in the previous slides can be controlled by controlling these 7 hazard control items from 1 to 7. As a result of safety design activities, relationships of hazards, hazard causes, and hazard controls shall be summarized, for example, in the way described in the table below, so that the progress of safety design and verification can be traceable. The identification and verification status of the hazard controls are confirmed by safety reviews of the satellite project. So this slide finally summarizes supplementary information about the safety design and review of thruster systems on CubeSat, released from the ISS. First, NASA's TOPO, the Trajectory Operations and Planning Officer team, will participate in an orbital operation safety assessment. And in case the CubeSat is equipped with thruster systems, it is necessary to pay attention to the fact that there are more review processes than satellites without thruster systems, and hence it takes longer to complete the entire review process. The use of software to control hazards requires CBCS, computer-based control system review. Strict design reviews will be carried out from the following aspects. So whether the hazard control is cancelled if the memory contents are changed due to SEU, etc. Whether abnormal commands can be detected and rejected. Whether appropriate exception handling being performed, and so on. When performing hazard control after release, it is easy to use microcomputers or logic devices, but in that case, it is necessary to demonstrate that no matter how much they malfunction, hazard control will not be disabled. So CBCS can be applied not only to thruster systems, but also to other hazard control. So conversely, if you have a high-performance computer that supports CBCS screening, the number of hardware hazard controls can be reduced. So after all the discussion about the safety design of the satellite, now I'd like to explain about the verification and documentation in the next chapter. So first of all, the verification process of a satellite can start from a breadboard model, BBM, so concept verification, before detailed design solutions of the satellite are verified using engineering model, EM. So once completed, a flight model, FM, is manufactured based on the verified design through the EM. And the minimum required tests are applied to obtain qualification for the launch. Sometimes a mechanical test model, MTM, is utilized before manufacturing the structure of the engineering model, or EM. So these verification processes of a satellite are illustrated in a diagram, together with the pictures seen on the right side. The first image illustrates system integration of the satellite, while the second and third images show the thermal vacuum test and vibration tests, respectively. For safety design and verification activity of satellites, the traceability of the safety requirements, their controls, and their verification results are indispensable. The relationship between them shall be traceable for the evaluation of the safety design at each safety review. So in this slide, I have illustrated the traceability of safety design requirements for the panel deployment mechanism as an example. The driving requirement says that unexpected panel deployment is classified as catastrophic hazard. So this can be regarded as one of the many hazards you have identified related to your satellite. Then, after this identification of the hazards, you need to analyze what could cause this hazard. In this example, you have identified electrical failures and mechanical failures as the causes, as illustrated on the right-hand side of the requirement connected to it. Then the control method shall be identified as illustrated in the third column. For example, 3 electrical inhibits shall be implemented against electrical failure. And also, those switches shall be mechanically tested by vibration tests as indicated in the fourth column. And finally, as illustrated in the fifth column, the corresponding verification methods and results shall be documented. For example, verification of the electronic circuit design is done by drawings, and mechanical verification shall be done by means of engineering and flight model vibration tests, planning, and actual tests, as indicated here. So here it is very important that the test plan is also a part of the verification documents, as this shall be evaluated by the safety review before conducting the actual test. As also indicated in the figure, so these items listed shall be, in general, identified with corresponding ID numbers, and the relationships between them shall be kept tracked. So in this slide, I have listed the required documents to be prepared and submitted to JAXA for CubeSat deployment from the International Space Station. There are some other documents as well. The templates of these documents are available at the link described below. So please refer to them at your earliest convenience. One of the most important tests of a CubeSat is the fit check. So in this test, a CubeSat's mechanical and electrical compatibilities are tested using the mechanical fit check model of the CubeSat deployment pod. The manufacturing and integration of the mechanical system shall fulfill the mechanical requirements posed on CubeSats, such as dimension tolerance, surface accuracy, contact of mechanical switches, etc. So not only the structural design, but also the satellite integration process shall be planned in a way that satellite assembly and integration processes are reproducible. It is very important that the assembly, integration, and test results are carefully recorded in documents. These documents are also input information for the safety and design reviews. Finally, I'd like to talk about the mission assurance of the CubeSat in the next chapter. First of all, applying a redundant design is one way to improve the system reliability. There are several types of redundant design approaches, such as cold redundancy, hot redundancy, and functional redundancy. So these are illustrated below. Cold redundancy introduces redundant or spare components such as two star trackers, as illustrated in this figure on the left side. Only the nominal component is used as default, and if it fails, the backup component is powered on and used. By the way, a star tracker is an attitude determination sensor. The hot redundancy introduces multiple redundant components, such as two star trackers, which are both used at the same time. They are used in the way that either component is used as default, or such that the accuracy or reliability of the system is improved by using both of the components simultaneously. So functional redundancy is another type which incorporates backup operations. So in this example below, the combination of a sun sensor and magnetometer is used to determine the satellite attitude as a backup should the primary star tracker fail. So due to the limited resources of CubeSats or small satellites, implementation of functional redundancy as much as possible is an effective manner to improve system reliability. It is also noted that some of these kinds of functional redundancy designs can be implemented by simply improving the onboard software. So in this next slide, I'd like to discuss the importance of reducing inhibit components in order to achieve a higher mission assurance for CubeSat systems. The number of components to be implemented as the inhibits for hazard control are dependent on the design approach of the satellite system, as illustrated in the figure below, and shall be kept to as few as possible in order to increase mission assurance. So in this example, the left side design solution is less reliable due to the large number of components based on a full triple redundant design. And on the contrary, the right side design solution has more reliability due to the minimum number of hardware components among the three. So it is important to reduce the number of components to achieve a higher reliability. Also, for mission assurance, planning and conducting solo functional tests is a key to ensure mission success, in addition to the tests required for safety assurance. The types of tests related with functional evaluation are the electrical tests, deployment tests, environmental tests such as vibration test or shock test, thermal vacuum test, radiation test, etc., and electrical end-to-end tests, hardware in the loop tests, measurements such as antenna pattern measurement, magnetic moment measurement, and electromagnetic compatibility test, launcher interface test, etc. Some of these are illustrated in the figures on the right. So this image is a scenery of electrical functional tests conducted in the lab. So this is an outlook of the ground simulation environment over Tohoku University. And these are deployment tests of thin film deployment mechanism in normal, hot, and cold temperatures on ground. There are no rules about functional testing, so please be creative and conduct a sufficient tests in order to ensure the mission success of your CubeSat. In this next slide, I'd like to talk about technology readiness level, or RTL. For effective mission assurance activities of CubeSat, it is important to evaluate and track satellite components' technology readiness levels. Components with high RTL will contribute to mission assurance. In the table below, the definition of a technology readiness level is explained. So RTL ranges in a score from 1 to 9. So with light, proven technologies classified into RTL 9, followed by stepwise maturity levels of the technologies. So RTL 9, here at the top, is defined as actual model is flight proven through in-orbit operations until the expected end of life in the actual operational environment. RTL 8 is actual model demonstration is flight qualified through system plot flight test, PFT, or acceptance test, AT, in an operational environment on the ground. RTL 7 is qualification model is demonstrated through system QT, qualification test, in an operational environment with adequate margins on the ground. RTL 6 is qualification model validation done through component QT or PFT in the relevant environment on the ground. RTL 5 is engineering model validation in the relevant environment. RTL 4 is a breadboard model validation in laboratory environment. RTL 3 is analytical and experimental proof of concept is done. RTL 2 is technology concept and or application is formulated. And finally, RTL 1 is basic principles are observed and reported. So strategic step-by-step in-orbit technology demonstration through CubeSat projects for future missions are very important. From this point of view, it is desired that technological heritage be shared with the community to accelerate technology development and further utilization. In terms of the CubeSat mission assurance, I'd like to point out the importance of the stepwise development of satellites and satellite projects for new developers. The key phrase is start small, go big. So recently, CubeSats have become a major game changer in the world. So thanks to the technological advancements of small satellites, CubeSats are now no longer for education only, but for actual space development and utilization. Achievements obtained from smaller CubeSats can be directly applied to larger satellites or even more advanced missions. I want to emphasize that one new CubeSats bring everything within your reach. As you might be already informed, Japanese universities, which belong to UNISEC, the University Space Engineering Consortium, are leading space education programs through satellite projects. We have a variety of satellite projects as illustrated in this slide. You can see and understand that satellite projects can be effectively utilized for space education and training. And more importantly, we can utilize our technological heritage for future satellite missions. So actually, JAXA and UNISEC are now working closely together on the mission assurance activities for small space systems. The research results of the activities are summarized in following publications. The first one is the lessons learned for mission success of microsatellites in Japanese, which is published as a contract report from JAXA, available under this link. The second one is the Mission Assurance Handbook for the University-built Lean Satellite, which is available both in English and Japanese under the link below. We are very happy if these documents can be useful for the mission assurance of your CubeSat projects. So UNISEC is now expanding its range of activities to the world. The UNISEC Global was established in 2013 and already has 21 local chapters with 55 points of contact. The UNISEC Global also has a permanent observer status of UN COPOS. The policy of UNISEC Global is written here. So especially our vision, 2030 all, says that by the end of 2030, let's create a world where university students can participate in practical space projects in all countries. I would very much like to recommend you to be a part of this community. Lastly, I'd like to make an announcement about one of the activities that we, UNISEC, are doing in terms of mission assurance. So UNISEC is offering a series of lectures for space development and utilization. So this includes not only space engineering, but also related topics such as space law and businesses. So currently, these lectures are held in Japanese, but we are now planning to establish an English curriculum which can be accessible online. So if you are interested, please keep being informed. Now I'd like to conclude my presentation with a summary of the content we have covered. So in this lecture, system engineering processes of CubeSats were introduced and an overview of their design and review processes are explained. Satellite subsystems classification, satellite development models such as BBM, EM, and FM, and related system engineering activities are described. Relationship of the safety and mission assurance S&MA activities together with launch vehicle compatibility were explained, and safety design requirements as well as the launch and release environment from the ISS was introduced. Detail of the safety design process was elaborated, and CubeSat safety and design reviews, precedence in safety design approaches, relationship between satellite development models and their design and safety reviews are explained. So types and severity level classification of hazards were introduced. The two major safety design methods were introduced, such as a fault-tolerant design and design for minimum risk. Examples of actual safety designs of CubeSats were introduced in terms of separation switches, electrical circuits, deployment mechanisms, wire mechanisms for deployment structures, and thruster systems. Verification and documentation activities related with satellite S&MA activities were explained. Related topics with CubeSat mission assurance were introduced, including redundant design methods, technology readiness level, strategic in-orbit demonstration approach, and space engineering education activities of UNISEC. Thank you very much for your kind attention.